So we're going to look at the Bohr model of the hydrogen atom. So we have if you remember, we had the atomic emission spectrum for the hydrogen atom. Atomic emission spectrum. And that this was going to be 4 lines. So we had a violet line, we had a blue line, we had a green line, and we had a red line. So we had these just 4 emission bands, and what Bohr did is he made a mathematical model that related these. And so what Bohr saw was that the energy of these lines had a 1/n² relationship. And so if we look at this, what does n mean? So if we have an energy level diagram here, energy that we start off at the bottom, n equals 1, where we would say energy to the n value equals 1, and then we have n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and then up and up. We'll do one more. N equals 7. There's a lot of these pictures in your books and online. But the point of this was that there was this relationship that the energies got, the spacing between energies got smaller, and this was this 1/n² relationship, and that you could actually look at the energy and associate that with a experimental value. So we have e to the n. So again, this is a proportionality, but how do we make it an inequality? Is we have e to the n equals negative 2.178 times 10 to the negative 18 joules 1/n². So this relationship between the n values, between 1 and 2, this value of the different energy levels was associated with this constant times 1/n². So this constant will have a couple iterations, but this is going to be defined as the Rydberg constant, RH. And this is the one that I'll use. You can actually group this constant together with a couple other, with Planck's constant and the speed of light, to make another term, and some people refer that to the Rydberg constant, but this is the one that's truly unique to this equation. And so what it means is we have, if we go back to these 4 lines, what those represent are, well, we'll start off with the red. Red was a transition from n equals 3. Again, emission is emitting a photon, so red was from n equals 3 level to the n equals 2 level. Remember that with these discharge lamps, we are exciting the electrons in these energy levels up to very high energies, and then when they relax back down, they emit light, and that's what we're seeing. So we see that n equals 3 to n equals 2 is red. If we look at the green is going to be from n equals 4. The blue is from n equals 5. And the violet is from n equals 6. Okay, and so the highest energy is going to be the largest transition, so n equals 6 to n equals 2. And so the 4 I've just drawn, these are called the Balmer series. The Balmer series, you'll notice that these don't go down to n equals 1. And the reason why is that the n equals 1, so if we do this, n equals 1, so if we go here, 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 and here, what's in pink, these are called the Lyman series, and they're all in the UV. So there's too much energy, so it's going to be higher energy. That's going to be the UV light is emitted, and we can't see that. So the only visible light we can see is going to n equals 2. Again, this n equals 2 to n equals 1 gap is really large, and so that's going to have too much energy for us to see. So we just focus on the Balmer series, but this is showing us that the only allowed transitions are occurring at, and that the energies of these different levels could be calculated using this emission spectra. So we start off with this emission spectra. We then are able to look at the energy, wavelength of light, calculate an energy using this constant. And so now we have the energy for n equals 1, 2, 3, and 4 for hydrogen. Okay, so then we can calculate energy level differences and then back calculate what photons need to be absorbed to go between energies and vice versa based on this experimental data. So we're going to take this this equation, and we are going to come down here with it, and we're going to say that, well, what's the delta E? So if we're looking at red, if we want to calculate the wavelength of this, or the energy of the photon that is emitted from n equals 3 to n equals 2, then that's going to be a delta energy, and that is equal to Rydberg constant negative. Now, let's see. I have negative there. Negative 2.178 times 10 to the negative 18 joules. Again, this is energy. And then 1 over n final squared minus 1 over n initial squared. Now, what you'll notice is that this is negative, and this is because for emission, so if you look here, emission, if we're going from 3 to 2, then we are going to have emitting energy, so that should be negative. So this is showing emission of energy, which in this case is a photon. Okay, so when the final is less than the initial, we get that this negative term. Okay, so this is a very useful equation. So we can look at the delta E and say, well, let's going from E, delta E is E final minus E initial. So if I go from, if I'm looking at going from E, I'll do it this way, 3 to n equals 2, that should be for red light. This is the change in energy. Then we would have the final n value being 2 and the final initial being 3. So we can figure out what that is. So this is only, so kind of a key caveat here is that this experimental value, this right here, the Rydberg equation, is only valid for hydrogen. Only valid for the hydrogen atom, or more specifically, 1 electron atoms. So you could have like helium has 2 protons, but if you get rid of a proton, then that would work. So you could have also lithium has 3 protons, get rid of 2 electrons, then it becomes a 1 electron system. So this only works for 1 electron systems, hydrogen being the most popular, but you can create some others. So this is only true for those. 2 electrons have repulsion, it becomes a lot more difficult. So let's go and put this into use. So let's just do the example we just had, where we had let's go from delta E n equals 4 down to n equals 2. So that would be E2, E4. We're going to have an emission, and we would like to figure out what this change in energy is. And so for the hydrogen atom, of course, so we have delta, it's right here, So it's equal to negative 2.178 times 10 to the negative 18th joules. And then we're going to have 1 over, so this is final, where we end up is 2, so that's 2 squared, minus 1 over the initial, which is 4 squared. And so if we do this, this is 1/4 minus 1/16. And now you'll notice when the bigger number is on bottom, when you square it, the fraction, this fraction is smaller, so that this number is positive, so that the sign still maintains its negative value. So if we do this, this value is 0.1875. And so if we multiply that by the Rydberg constant, we get a value of, so delta E of negative 4.08 times 10 to the negative 19th joules. Again, the negative is showing us it's an emission process. So energy is released, the sign is negative. But sometimes people like to report this in terms of wavelengths. And so we know that E is equal to hc over lambda. And so if we have delta E is equal to negative, well, I'm just going to use, delta is negative 2.18 times 10 to the negative 18th joules. What we're going to do is we're going to sub this in, and so we get times our parenthesis here, so we get 1 over lambda, and then move this hc to the bottom, is equal to negative 2.18 times 10 to the negative 18 joules, and then divided by hc. Now, what some books like to do is they like to bunch all this together and put a number in here, because none of these values are changing, and you get 1.09 times 10 to the 7 inverse meters. So that's what happens when you take Planck's constant times speed of light divided by this value here. So this is negative as I've written it with the 1 over n squared final minus 1 over n squared initial. Another funky thing that some books will do is that they are actually going to switch these to get rid of the negative sign. So I just want you to be comfortable with this. When this equation is written as a wavelength, and there's actually a really good reason why. I'm going to write it out first, and then I'll explain the reason why. So they're going to make this positive, so it'll be a positive 1.09 times 10 to the 7 meters to negative 1, and then what they're going to say is 1 over n squared low, the lower of the two numbers, is like an absolute value over 1 over n squared high. Now, this is an equation, so remember 1 over lambda is like that, we call it a wave number, and it'll have units of inverse meters. Now the reason why is because if you didn't make this positive right here and you were calculating for an emission of a photon, you would get a negative value for the wavelength. And we all know that you can't have a negative value for the wavelength. If you put down a negative value for a wavelength, that does not make any sense. We really want to avoid that because your instructor would be very sad. I'd be grading an exam, for example, and I see a negative wavelength, and I would be like, I can't believe that my students think that you can have a negative wavelength. That's physically impossible, and I get sad, and when I get sad, I go to a dark place, so like a closet, and I start crying because I'm so sad, because I try so hard, and sometimes it doesn't work, and then my kids are like, Daddy, why are you crying? And then I say that my students think that we can have negative wavelengths, and then they start crying because I'm crying, and then everyone starts crying. And so we wanted to avoid this and all this crying by just not putting a negative sign in front of things that are physically impossible. You can't have a negative mass, you can't have a negative volume, you can't have a negative wavelength, okay? So what this equation does is it eliminates that possibility by basically making an absolute value in that the wavelength of a photon emitted or absorbed is the same value in these problems, and so you do not need to have the sign. And so these are just given as if you put the low lower value here, it's always going to be the bigger number if you take the fraction, and that's going to keep this value to be positive. So long story short, don't be confused when that's a positive value and the n has switched from final initial to low and high. That's simply when you have a wavelength. It keeps things positive, and we chemists like to keep things positive.